Hello everyone. Tonight, we will talk about a dark event in our cosmic backyard. An event that forced astronomers to question everything they think they know about what we can see in space. In August 2025, the most powerful eye humanity has turned toward the stars, the James Webb Space Telescope, found exactly the rare thing it was looking for in the deep universe. A Saturn mass gas giant orbiting Alpha Centauri A, the closest sun-like star to our own Sunday. This should have been one of the greatest discoveries in human history. A neighboring world only 4 light-years away, close enough that one day we might truly push the limits and actually visit it. But then something impossible happened. This newly discovered object seemed to dissolve into the darkness and disappear. The discovery and the mysterious vanishing that followed now stands before us as one of the greatest astronomical mysteries of our time. If you enjoy calm journeys that change the way you see reality, and if you haven't already, you can consider subscribing to the channel and liking this episode. Your support helps these deep explorations reach more curious minds. Now, empty your mind. Prepare yourself for the silence of the universe. We're beginning. Pause. This mysterious story does not actually begin in 2025. It begins billions of years ago, when 3 stars locked together by the relentless force of gravity came together in the cold, dark sea of space. We call this mesmerizing system Alpha Centauri. What makes Alpha Centauri so special for us comes down to one unshakable truth. It is close. Only about 4.3 light-years away, it is the nearest stellar neighbor of our Sun in the vastness of space. If you look up from the southern hemisphere on a clear night, you can see Alpha Centauri as one of the brightest points of light cutting through the dark. To the naked eye, it looks like a single, lonely star suspended in the cosmic void. But inside that single point of light are 3 separate stars, locked into a complex gravitational dance that has continued for billions of years. The largest member of the system, Alpha Centauri A, is a little bigger and a little brighter than our Sunday. Beside it is its partner, Alpha Centauri B, somewhat smaller and dimmer, about 85% of the Sun's mass. These 2 majestic balls of fire orbit one another in an elliptical rhythm that never ends. Sometimes they approach as close as about 11 times the Earth-Sun distance. Sometimes they drift as far apart as about 36 times that distance. And then, far beyond this chaotic pair, there is Proxima Centauri, a small red dwarf star traveling alone at an enormous distance from the main binary. As its name suggests, it is actually the closest star to Earth in the universe. But the center of our story is Alpha Centauri A, the main target of astronomers' planet-hunting obsession for decades. The logic was simple. If humanity is ever going to visit another star system, the first natural target for probes or even futuristic colonies would be this one, because it is near. Even with today's technology, such a journey might take decades or centuries, but it is not entirely impossible in principle. A probe traveling at just 1% of the speed of light could reach Alpha Centauri in roughly 430 years. That is far too long for a single human life, but theoretically, a craft launched from Earth could arrive after only a few human generations. When we look at other nearby stars, Alpha Centauri's unique value becomes even clearer. Barnard's star is about 6 light-years away. Wolf, 359, sits around 7.8 to 8 light-years away. In the cold reality of space, every additional light-year adds daunting decades, sometimes centuries, to any plausible journey. That is why Alpha Centauri became the natural starting point for our interstellar dreams. But before you sail into the dark unknown of another star system, you want to know what you will find there. Are there planets? If so, what are they like? And could any of them host life? Sending a priceless probe into a featureless emptiness with no potential and nothing to study would be an unforgivable waste of time and resources. That is exactly why astronomers have been searching for decades for the answer to a simple question. Does Alpha Centauri have planets? That question, simple on the surface, became one of the most exhausting tests in all of astronomy. Because finding exoplanets around other stars is one of modern science's most intricate puzzles. Planets do not produce their own light. They are tiny, dark worlds placed next to blindingly bright parent stars. Trying to see a planet right beside a sun-like star is like trying to spot a tiny firefly glued to the beam of a lighthouse from kilometers away. Over the last decades, astronomers developed clever methods to find these hidden worlds. The first is the transit method, watching a planet pass in front of its star, causing a small temporary dip in brightness. Another is the radial velocity method, detecting the subtle wobble a planet induces in its star as they orbit a common center of mass. But in Alpha Centauri, both methods struggle. The transit method requires near-perfect alignment from our line of sight. The radial velocity method faces a different problem. Alpha Centauri A is part of a complex binary system. The gravitational dance of A and B creates large signals that can mask the delicate wobble of any smaller planet. That leaves a third method more difficult than all the others: direct imaging. Instead of detecting a planet indirectly, direct imaging tries to take an actual picture of the planet itself. This is extraordinarily hard because planets are billions of times dimmer than their stars, and from our perspective, they sit almost right next to the star's glare. But technology advanced dramatically. In December 2021, the James Webb Space Telescope launched and began reshaping our view of the universe. Webb observes in infrared. In infrared wavelengths, planets can glow from their own internal heat, making them easier to detect in the dark. Webb also uses specialized instruments called coronagraphs, which block a star's intense light, like raising your hand to cover the sun while trying to see something faint nearby. And Webb operates at extraordinarily cold temperatures in deep space, allowing it to see extremely weak infrared signals with unusual clarity. Together, these features made James Webb the most powerful planet hunter ever built. In early 2025, an astronomy team proposed using Webb's unique power to search for planets around Alpha Centauri A. Alpha Centauri's closeness gives any planet there a larger apparent separation from the star compared to distant systems, making the hunt more feasible. The team focused on Alpha Centauri A, the most sun-like and most promising target. Observations continued for weeks through late spring and early summer before the autumn of 2025. Webb pointed its coronagraph toward Alpha Centauri A. At the same time, its infrared camera searched the surrounding darkness for faint companions. The observing program was designed with extreme care. The telescope was rotated between exposures to capture multiple images at slightly different orientations. This step is vital for separating real planets from false reflections and instrument artifacts. Internal reflections or detector imperfections rotate with the telescope. A true planet fixed relative to the star does not. The team also imaged the region in multiple infrared wavelengths. Planets have characteristic signatures at different wavelengths depending on temperature and atmospheric composition. By checking the faint point across several bands, they could test whether it behaved like a planet. Each session lasted for hours. Webb locked onto its target with astonishing precision, holding the star at the center of the coronagraph mask to within a tiny fraction of an arcsecond. Its guidance sensors made thousands of micro-corrections. Finding something hidden in darkness demands that kind of quiet perfection. The infrared detectors recorded millions of photons, but most were stubborn starlight leaking past even the best coronagraph. No technology can swallow all of a star's light completely. The bright, residual glow makes faint planets hard to see. The raw data were transmitted to Earth as enormous files. Scientists began a meticulous reduction process, removing background noise and modeling the star's scattered light with surgical precision. They subtracted the glares. And then, after all that mathematical cleaning, something emerged from the darkness. A faint but undeniable point of light sat about 640 million kilometers from Alpha Centauri A. The first reaction was cautious excitement. Could it be an equipment error? A ghost in the optics? The team ran extensive tests. The point held its position relative to the star even as the telescope rotated. They checked star catalogs and deep sky maps. This object was not a background galaxy or distant star. It was there, bound to Alpha Centauri A by an invisible gravitational connection. What was this new world? The spectrum across infrared wavelengths began to whisper secrets. There were hints consistent with thick atmospheres of gas giants, signatures resembling methane and water vapor. The brightness and thermal emission suggested a large mass. A Saturn mass gas giant, about 95 times the mass of Earth. By human standards, it was hot. By gas giant standards, it was relatively cool, glowing somewhere around 500 to 1000 Kelvin, perhaps radiating leftover heat from formation. Now imagine a quiet journey inward into that faint point of light. There is no solid surface to land on, only thickening layers of gas, descending deeper and deeper toward the planet's heart. Farther down, pressure becomes crushing. Gas behaves like fluid. Deeper still, hydrogen may become metallic, conducting electricity in an alien inferno. Perhaps at the very center, there is a small rocky core hidden under an ocean of hydrogen and helium. From the outside, you might even imagine a massive ring system, dust and ice, shaped by ancient collisions. But the most mesmerizing thought is that this giant might not be alone. It likely carried its own moons, like Saturn does. Perhaps one moon was Titan-like, larger than Mercury, wrapped in a thick atmosphere with dark seas of liquid methane. Or perhaps another moon was like Enceladus, hiding a warm subsurface ocean beneath an icy shell, venting water, ice, and organic molecules from fractures near its pole. If this new planet around Alpha Centauri A was real, then its moons, if they existed, could be entirely new worlds with their own potential for habitability. In August 2025, confident in the discovery, the team submitted its findings to a prestigious astronomy journal and announced the result publicly. They did not want to wait for the months-long peer review process. Their confidence in the signal was strong, and their excitement had a very human reason. If a Saturn-mass gas giant existed in the system, it likely was not alone. Protoplanetary disks typically form multiple planets. If this giant existed farther out, smaller rocky worlds might exist closer, possibly even in the system's habitable zone, the narrow region where liquid water could persist. That possibility, whispered rather than proven, was enough to shake the world. Headlines spread rapidly. Humanity's dream of becoming an interstellar species felt less like old science fiction and more like a destination. Space agencies began openly discussing bold projects, laser-driven probes, tiny sails, ambitious plans aimed at sending craft to Alpha Centauri at a fraction of the speed of light. Everything seemed to be unfolding perfectly. But the silent surprise the universe had prepared was only beginning. Pause. After the first wave of excitement, astronomers planned the next step quickly. Follow-up observations to track the planet's motion and measure its properties with far greater precision. If the gas giant completed an orbit in 2 or 3 years, watching it carefully over several years could pin down the orbital parameters. It could clarify the planet's mass. It might even reveal additional unseen worlds through gravitational interactions. To illuminate these unknowns, teams around the world lined up for James Webb time. Proposals flooded in. Different observing strategies, different infrared bands, different coronagraph configurations. Some aimed to obtain spectroscopy and read the planet's atmospheric composition in detail. Others hoped to detect moons, rings, or surrounding structures. James Webb's schedule is planned far in advance. Competition for time is fierce. Each year, thousands of astronomers request hours or hundreds of hours, fighting for a few precious windows. But the potential of Alpha Centauri was so extraordinary that follow-ups were given high priority. Only 2 months after the announcement, in October 2025, a different team took control of the telescope for their own observations. The golden mirrors turned once again to Alpha Centauri A. They used the same instruments and the same techniques, peering into the same dark region. The star was there as always, but something strange, something chilling appeared. The planet was gone. At the exact location where the gas giant had been detected just months earlier, There was now only deep, cold emptiness. In the infrared images, there was not even the faintest trace, no point, no glow, no hint. The team repeated every analysis they could imagine. They reviewed the reduction pipeline. They verified calibrations again and again. They scanned the entire region around the star with care. The result did not change. There was nothing. In November 2025, they reported this eerie situation in a paper that carefully stated what they observed more precisely, what they could not observe. They did not claim the original team was wrong. They simply reported their own findings. Something that appeared present in May and June seemed to have vanished by October without leaving a mark. The astronomical community erupted. Social media, scientific forums, and academic circles filled with arguments. Some defended the first detection fiercely. Others were skeptical. Many agreed only on one point: more data was needed. The question that gnawed at every mind was simple and dark. How can a Saturn-mass planet disappear? Planets are not small objects that can simply fade away. A structure held together by gravity, 95 Earth masses of hydrogen and helium, does not vanish according to the laws of physics. If such a body were destroyed, it would require a catastrophic collision on an unimaginable scale. But even then, a collision would not leave silence. The debris-heated gas and dust would glow for years, perhaps decades, in infrared. It would not erase itself neatly from the sky. Yet Alpha Centauri A showed no sign of catastrophe. The follow-up observations revealed only a quiet star and ordinary darkness. Faced with this impossible quiet, the community did what science always does in the presence of an anomaly. It generated hypotheses, evaluated the limited evidence mercilessly, and searched for new ways to test reality. The first and simplest explanation was that the original discovery had been a false positive. Perhaps what the first team saw was not a planet at all. Perhaps it was an optical reflection, a subtle artifact, or a background object misidentified. False positives are one of the greatest dangers when searching for faint companions near blinding stars. The history of astronomy is filled with announcements that later collapsed under scrutiny. In the 1960s, when the first regular radio pulses were detected, some scientists briefly wondered if they were signals from an alien civilization. They turned out to be rapidly spinning neutron stars' pulsars. In later decades, stellar activity sometimes mimicked planet signals. Some early planet claims were later retracted. But modern space telescope standards are far stricter. The original team rejected the false positive accusations strongly. They had analyzed the data with exceptional care. They had cross-checked internally. They had tested instrument behaviors. They argued the statistical strength of the signal made random noise extremely unlikely. And the object behaved like a real planet. It stayed fixed relative to the star as the telescope rotated. It appeared in the right wavelengths. It resisted the usual signatures of instrument artifacts. How could an artifact mimic a planet perfectly, then vanish completely months later? The second hypothesis involved orbital geometry, a shadow play of mechanics. Perhaps the planet was real, but from our viewpoint, it had moved behind the star and become hidden. Occultations happen in our own solar system. Venus and Mars can pass behind the Sun, disappearing from view. When Mars is behind the Sun, radio signals can be disrupted and communication becomes difficult. Could the same thing have happened here? But the mathematics refuse to cooperate. Orbital mechanics lets us predict motion with extraordinary precision. At a separation of roughly 640 million kilometers, a full orbit would likely take 3 to 4 years. Between May and October, the planet would have moved only a modest amount along its path, nowhere near enough to slip behind the star unless the orbit were aligned with implausible perfection. For the planet to hide fully, the orbital plane would need to be almost razor-thin from Earth's perspective, and the timing would need to land exactly within that 2-month window of follow-up observations. Too many coincidences piled on top of one another. The third possibility was darker, a violent event between the two observations. Could something have destroyed or disrupted the planet? Planet-planet collisions are not absolutely impossible, but they are extraordinarily rare in mature, stable systems. Such chaos is expected early in a system's youth, when orbits are still unstable and bodies are still colliding or being ejected. Alpha Centauri A is roughly as old as our Sun, billions of years old. In such a settled system, a late catastrophic collision would be astronomically unlikely. And again, a collision would glow. The aftermath would be bright and long-lived in infrared, but the star remained ordinary and calm. As physical explanations weakened, suspicion drifted toward our own instruments. Perhaps there was no false positive and no cosmic catastrophe. Perhaps the planet was still there, but something in the second observation had gone wrong. Space telescopes are astonishingly complex machines made of hundreds of delicate components. A tiny deviation can erase a faint target. If the coronagraph mask is misaligned by a minute amount, by a fraction of a pixel, starlight leaks, floods the background, and swallows a faint planet in glare. Could the planet have cooled rapidly and become invisible? That seems unlikely. Gas giants cool slowly over billions of years. Jupiter and Saturn still carry internal heat after 4.5 billion years. A few months cannot extinguish a gas giant's thermal emission. Could atmospheric features have rotated a darker hemisphere toward us? Gas giants are not uniform. Their atmospheres contain storms and bands. But such variations do not normally erase a planet completely. Could cosmic rays have damaged detectors, creating or removing signals? Could a subtle contamination on optics or a software reduction error have played a trick? These possibilities were investigated, but the telescope's health looked normal. There was no clear performance drop, no obvious fault. And so the mystery deepened. The most haunting hypothesis was also the strangest. What if the planet was real and had become temporarily invisible? It sounds like science fiction. A world turning invisible feels absurd. But in space, even absurd-sounding ideas can have physical mechanisms. One possibility involved dust. Space is not perfectly empty. Even between planets, there can be thin haze of gas and dust. In some systems, dust concentrates into rings or clouds. If Alpha Centauri A had an unseen debris structure, Perhaps the planet passed through a denser region that absorbed or scattered its infrared emission, making it appear faint or invisible. But this theory had gaps. If there were enough dust to hide a planet, the dust itself might be heated by starlight and show up in infrared. Webb should have detected a clear excess signal, and the timing problem returned again. Debris structures do not drift like weather clouds. If the planet's orbit crosses a dense region, the dimming should be periodic, repeating every orbit, rather than coincidentally striking only during our short observing window. That pushed some scientists toward a more unsettling idea. The cause might be internal. Gas giants are not quiet spheres. They have no surface to stand on, only deep, churning atmospheres. Winds can reach terrifying speeds. Storms can cover areas larger than Earth. In our own solar system, Jupiter's Great Red Spot has persisted for centuries. Neptune has shown giant dark storms that appear and vanish within years. Could extreme atmospheric changes hide the planet's thermal emission? Webb was hunting infrared heat, the planet's internal warmth leaking into space. If the upper atmosphere suddenly formed a global layer of cold, thick clouds or haze, it could act like a blanket, trapping heat and muting the outward infrared glow. In that case, the planet would not be gone at all. It would still exist, still orbiting, only wrapped in a temporary atmospheric cloak that made it appear dim or invisible from afar. This scenario would be dramatic, and it would imply that exoplanets could be even more dynamic and unpredictable than we imagined. But it also raised another problem: timescale. Seasonal and atmospheric shifts on gas giants usually unfold over months, years, even decades, not in a few weeks. For a planet to become effectively invisible within 8 weeks would be beyond anything we have ever confidently observed. Still, as ordinary explanations ran out, even the strange ones deserved a serious look. At this point, the only honest path forward was the simplest. We had to look again. Pause. In December 2025 and the weeks that followed, astronomers across the world began pushing for a third, deeper observing campaign. What happened next became a rare moment in modern astronomy, an unusually unified global effort. Under normal conditions, obtaining time on James Webb is brutally difficult. Thousands of researchers compete for short windows. But the Alpha Centauri mystery changed the rules. The scheduling committee used a special initiative and allocated additional time outside the usual plan. The system received urgent priority. This new campaign was more strategic than the previous ones. Teams coordinated carefully so they would not repeat the same mistakes. The goal was not merely to see the dot again, but to hunt for it across the infrared spectrum and across instrument configurations. Some teams used near-infrared instruments optimized for warmer targets. Others relied on the mid-infrared instrument, designed to detect much cooler thermal traces. The plan was clear. If the planet had shifted its emission to different wavelengths, if it had cooled, or if its atmosphere had changed, we needed to cover every plausible band. The coronagraph configuration also became a focus. Different masks and settings trade off between blocking starlight strongly and allowing access to regions closer to the star. A configuration that is perfect for distant companions might be blind to closer ones, and vice versa. Astronomers tested multiple setups with patience, refusing to let a simple configuration mismatch be the reason a planet vanished. There was also the quiet battle against Webb's own physical limits. Even in deep space, temperature is never perfectly constant. Small changes in spacecraft orientation can create tiny thermal shifts. For ordinary observations, such details are negligible. But when you are trying to detect a ghostly signal just a few pixels from a bright star, microscopic changes can matter. So the campaign was timed and structured to sample different conditions, different angles, different thermal states, building a layered picture instead of relying on a single snapshot. Weeks passed. Data arrived on Earth. Computers ran complex algorithms. Exhausted scientists stared into numbers, searching for meaning. And then the first results appeared. They did not bring comfort. They made the mystery worse. In the final days of 2025, analyses of the new data revealed something deeply confusing. In the same region where the gas giant had first appeared, a faint point of light returned. Yes, it was there. It moved with the star, still showing signs of being bound. But something fundamental had changed. The light was far weaker than before. More than half of its earlier brightness seemed lost. And then came the next shock. Within the same observing program, within hours or days, the signal sometimes disappeared again. In one set of frames, it was present as a ghostly point. In another set, it was absent, leaving only emptiness. Later, it returned again, dimmer, unstable, almost flickering. The object began behaving like a broken lighthouse in the void. One day, it reached perhaps 30% of its original brightness. 3 days later, there was nothing. A week later, it returned fainter and slightly shifted within uncertainties. In exoplanet imaging, this kind of irregular on-off behavior has no clean, established counterpart. Of course, the universe contains objects that vary in brightness. Variable stars pulse, eclipsing binaries dim in predictable rhythms. Explosions flare and fade over months. But planets are expected to be stable emitters on these timescales. In our solar system, cloud patterns can cause modest changes, small percentages. No known planet triples its brightness and then drops to zero within days. If this was truly a planet, it was challenging what we thought we understood. At that point, researchers began studying not only what was seen, but what was not seen. A non-detection is information. If an instrument looks and finds nothing above a certain threshold, that sets limits on the object's brightness at that moment. Was the original detection a temporary flare? That seemed unlikely. A supernova, only 4 light-years away, would be blindingly obvious to the naked eye. Venus bright, or brighter, an event that would affect Earth's sky in unmistakable ways. A small collision would not create a long-lasting infrared point that mimicked a planet. The community split more sharply. Some insisted the signal was real and represented a physical world whose emission was being modulated by an unknown process. Others argued the flickering was simply noise hovering at the edge of detectability, random fluctuations that sometimes crossed the threshold and sometimes did not. A third group suggested something stranger, perhaps a cloud of dust, a disrupted object, or an unusual structure that could mimic a planet at certain times. And beneath those debates lived a deeper truth about science. Progress is not a smooth, clean staircase from ignorance to certainty. It is often messy, contradictory, exhausting, full of arguments and repeated tests. And sometimes the answers arrive slowly, years after the first spark. Astronomy's history is full of such stories. The planet Vulcan, near Mercury, was once claimed by respected observers. It appeared and disappeared, and was later understood as error. The famous claim of possible microfossils in a Martian meteorite sparked global headlines. Then, years of debate. Even decades later, arguments remained. The Alpha Centauri flicker could follow the same path. It could be confirmed, it could be rejected, or it could remain suspended in ambiguity for a long time. And this brings us to a quiet philosophical question. When does a discovery truly begin? If a team sees a faint companion and passes every test available, is that a discovery? Most rules would say yes, but if follow-ups fail, does the discovery vanish? Or does it reveal a world whose behavior is beyond our simple expectations? This is not a purely academic debate. It affects telescope scheduling, funding, future missions, and interstellar ambitions. It affects how future astronomers are trained and how the public trusts the process of knowledge. If we demand that only discoveries confirmed years later count, we risk silencing early signals and slowing progress. But if we treat every first hint as absolute truth, we invite disappointment when the universe refuses to cooperate. Most astronomers choose a more mature middle ground. Science is a living process. Early results open questions. Questions drive better measurements. Better measurements sharpen reality. Alpha Centauri A's ghostly point now sits in that gray zone between darkness and certainty. Pause. Now, let's step back to something we know with far greater confidence about Alpha Centauri. We know the system contains 3 stars, and we understand their masses and orbits well. And we know with great certainty that Proxima Centauri, the small red dwarf, has planets. Proxima b, discovered in 2016, is roughly Earth mass and sits in the star's habitable zone. Other candidates and detections point to additional worlds as well. These are stable signals, confirmed repeatedly with multiple techniques. That certainty makes the Alpha Centauri A mystery more striking. We know the system can form planets. The question is, what exists around the Sun-like star A? And here, the system's gravity becomes crucial. Alpha Centauri A and B orbit closely enough that their gravitational influence creates strict stability limits for planets. Simulations indicate that stable orbits around Alpha Centauri A likely exist only out to a few astronomical units around the scale of our own asteroid belt. Beyond that, the pull of Alpha Centauri B can destabilize or eject planets over time. This is where the August 2025 claim becomes eerie in a different way. The faint object was reported at around 2.7 astronomical units from Alpha Centauri A, near the outer edge of the stable zone. Not at a random location, but right where orbital mechanics would allow a planet to survive long-term in this binary system. That detail is one reason the discovery seemed so compelling. The signal appeared exactly where a real planet could plausibly exist. If the planet is real, its importance is profound. A Saturn mass gas giant would imply a rich protoplanetary disk in Alpha Centauri A's past enough material to build not only rocky worlds, but massive gas bodies. And where there is a giant planet, there can be structure, gravitational organization, and perhaps even a kind of shielding effect for inner regions, the way Jupiter influences the architecture of our own solar system. And then there are moons. In our solar system, the most intriguing habitability candidates are not only planets, but icy moons, Titan, Enceladus, Europa, places where chemistry and water might hide beneath ice and darkness. A gas giant around Alpha Centauri A could host moons that become prime targets for future exploration. But if the signal is ultimately a false positive, that outcome is not failure. False positives teach us where our instruments and analyses can be fooled. They help us refine techniques, improve pipelines, and understand noise sources. That is how science hardens itself against illusion. And either way, this mystery will not remain unsolved forever. Because new eyes are coming. On Earth, in places like the high deserts of Chile, extremely large telescopes with 30 to 40 meter mirrors are rising, paired with adaptive optics that correct atmospheric distortion. In space, next-generation observatories designed to directly image Earth-like planets are being planned. These instruments will push beyond today's limits, blocking starlight more perfectly and revealing fainter companions more reliably. If a Saturn mass planet is there, these machines will eventually pull it out of the darkness. Pause. Now we move to the part of the story that quietly changes everything. What such a nearby planet would mean for actual interstellar travel. Alpha Centauri is often described as close. 4 light-years can sound almost comforting, like a neighbor just beyond the fence of our cosmic backyard. But in the cold, unforgiving reality of space, 4 light-years is an abyss. Imagine leaving the outer boundary of our solar system and sailing toward Alpha Centauri. Ahead lies trillions of kilometers of darkness. Even light racing at 300,000 kilometers per second needs more than 4 years to cross it. Now imagine using our best chemical rockets. They took us to the moon. They sent probes to the far edges of the solar system. But for an interstellar journey, that technology is like trying to cross an ocean in a fragile raft. With today's fastest spacecraft speeds, reaching Alpha Centauri would take tens of thousands of years longer than the span of all recorded human civilization. So if we ever go, it will require new ideas that seem almost unreal. One concept imagines probes traveling at about 1% of light speed. That still means centuries, about 430 years. But other proposals aim higher, around 20% of light speed. How? Not with giant fuel tanks, but with tiny craft nanoscale probes perhaps the size of a postage stamp, pushed by enormous laser arrays that fire concentrated light at a sail. Light carries momentum. A powerful enough beam, focused long enough, could accelerate a sail to incredible speeds. If such technology becomes real, the journey to Alpha Centauri could shrink to about 20 years. 20 years is long, but it fits into a human lifetime. It becomes a time frame in which results could arrive while the people who started the mission are still alive. But before you launch something so ambitious, you need certainty. You cannot fire humanity's most extreme engineering project into the void without knowing what you are aiming at. You need a target worth the effort, a world worth the risk. That is why the flickering signal matters. The lost planet is not just a curiosity. It is potentially a compass for our first real step toward another star. Now imagine those tiny emissaries, pushed by light, leaving home. They first face an invisible boundary, the edge of our sun's protective bubble, the heliosphere. The sun does not only emit light and heat, it also breathes a continuous storm of particles called the solar wind. This wind creates a vast magnetic domain. Far out, that domain collides with the cold gas of interstellar space, forming an active boundary layer. Voyager 1 and Voyager 2 crossed this boundary and measured changes in plasma density and magnetic fields. They became the first human-made objects to enter interstellar space. But those Voyagers traveled at about 17 kilometers per second. A probe moving at 20% of light speed would slam through interstellar space in a fundamentally different regime. At those speeds, even a grain of dust becomes lethal. The kinetic energy is enormous. A tiny collision can be equivalent to an explosive impact. Engineers propose sacrificial shields, protective folding sails, and hardened microelectronics. But there is no perfect defense. At such speeds, you cannot dodge. You can only endure. And then comes communication. A gram-scale probe cannot carry a large radio dish. It might send data back with a tiny laser, but a laser beam spreads over distance. After 4 light years, the signal becomes a whisper. On Earth, vast detectors would need to stare for years to catch it. And then there is time. 20 years to arrive. Then the light speed delay, about 4 more years, for the signal to travel back. People who launched the mission may wait nearly a quarter century for the first results. A test of patience, not only of technology. Now, picture the encounter itself. At 20% of light speed, the probe cannot stop. It will pass through the system like a bullet. The entire scientific harvest will happen in a few hours, perhaps minutes, while the craft races past the star and its worlds. In that brief window, cameras would fire thousands of frames. Sensors would try to read atmospheric signatures. The craft would look for moons, rings, dust structures, anything that could explain why a planet seemed to appear, disappear, and flicker. If the planet is real, those images would show storms, bands, layers of cloud. If it has moons, they might appear as tiny moving points. If a dust structure hides the planet at times, sensors might detect the density and composition of that veil. If the planet is not real, if the original signal was illusion, then the probe would send back an emptiness so clear that the debate would end in one quiet moment. Either way, the truth would finally harden. But for now, the truth remains at the edge of what our instruments can hold. A faint point beside a bright star. A flicker in the darkness. And that flicker has taught us something vital. Even with our most powerful telescope, directly imaging planets near bright stars is still a frontier. At the frontier, the universe can look like it is playing games. The difference between real world and instrument ghost can be unbelievably subtle. That is why independent confirmation matters. That is why science repeats itself. That is why it argues. Not because it is weak, but because it refuses to pretend. Pause. Now let's return to something calm and solid. If you live in the southern hemisphere, you can step outside on a clear, dark night and see Alpha Centauri, a slightly golden point of light hanging among other stars. It looks ordinary, but it is not. It is close, so close that its light reaches your eyes after only a little more than 4 years of travel through cold space. It is close enough that we can measure its spectrum precisely, track its motion, and, with enough patience, pull out the faint signature of worlds that orbit it. If planets exist there, their hiding places are shrinking. With today's tools and tomorrow's even sharper eyes, we will find them, or we will learn exactly why we cannot. The story of the disappearing planet is not over. It is only beginning. More observations will be scheduled. More data will arrive. More papers will be written. Perhaps 5 years from now, we will look back and celebrate August 2025 as the first footprint of a confirmed exoplanet next door. Or we will remember it as a historical lesson in how easily instruments at the limit can deceive us. Maybe the debate will last longer. Maybe the evidence will remain stubbornly ambiguous for years. But the search will not stop. Because we have to know what is there. We have to know what kinds of worlds orbit our closest neighbor. We have to know whether any of them could carry oceans, atmospheres, or the delicate chemistry of life. These questions will help determine whether humanity remains confined forever to a single solar system, or whether we will eventually cross the dark sea and spread toward the stars. And now, it's time to slow down. Just as those tiny probes would surrender themselves to years of silent travel through darkness, you can let your mind travel into quiet. The noise of the day is far behind you. The urgent thoughts, the unfinished tasks, the heavy conversations, all of it is now at a distance you do not need to cross tonight. You do not have to solve anything right now. You do not have to reach anything. You are safe. Now gently close your eyes as if you are looking into the deepest darkness of space, soft, wide, and endless. Feel your body become lighter, as if gravity is slowly loosening its grip, like a spacecraft easing away from the shore of the world. Your bed is your own private starship, carrying you into the calmest corner of the universe. Take a deep, slow breath. Imagine you are breathing in the ancient, clean light of distant stars. And as you breathe out, feel the weight in your shoulders, your neck, and your mind releasing quietly without effort. Those weights drift away like cosmic dust, dissolving into the black. Your body can sink gently into rest while your thoughts float upward, soft and distant. The silence of the universe is not an empty terror. It is a gentle, dark blanket covering you, protecting you, letting the sharp edges of the day fade. Somewhere far away, worlds orbit in steady, patient loops. They have been keeping their calm rhythm for billions of years. They have no urgency, no panic, only motion, balance, and time. Your thoughts can follow that rhythm now. They can become slower, dimmer, like a faint signal crossing interstellar space until they blend into the quiet. Time loses its sharpness in this place. There is only now, only your breathing, only the steady pulse of the cosmos. Let yourself sink into that pulse. Let the universe hold the parts of you that feel tired. Let the darkness be soft. Let the silence be kind. And as you drift closer to sleep, remember, the answers out there will come in their own time. The universe does not rush. It reveals itself slowly to the minds that return again and again with patience. For tonight, you don't need the answer. You only need rest. Sweet dreams.